In section 2.2, we will be verifying trigonometric identities. So to verify an identity, we'll just be proving the equation, so showing that it's true, that the left side is indeed equivalent to the right side. I'm going to share with you some strategies. I put a document in the supplemental resources, but some good things. Well, first, always try something. These do take a lot of practice and a lot of experience to kind of recognize what might work and what might not work. So always try something. Even if it doesn't get you to the answer, it might help you figure out what will. Try working on one side of the equation at a time, and it's usually better to work with the more complicated side first. Look for anything that you can factor. Can you add some fractions? Can you simplify a denominator? You want to see if there are any identities that you can use to simplify things. Sometimes it's helpful to write everything in terms of sine and cosine. Not always, but sometimes that will. See if you can factor, anything you can substitute. Can you find a common denominator and add two fractions together? Always cancel. If there's anything you can cancel out, be on the lookout for that. Multiplying by conjugate sometimes something that will be helpful. But again, practice, 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 because these can be solved more than one way, and it takes a lot of practice to get an idea of which techniques you should use. So let's get into it. All right, so here we have an equation, and so I'm gonna work with the more complicated side, the one that has more terms, so more going on, which in this case is the left side, and I already know what it should equal. So I'm just trying to simplify it until I get to sine squared theta. As I'm solving this, keep in mind that this is not the only way, not even necessarily the best way. Sometimes, I'll make it work and get to the end, and I think I could have done that much simpler. So if your mind is taking you somewhere else, I encourage you to try that and see if you can get all the way to sine squared theta. You do not necessarily have to do it my way. All right, so first up here, looking at these two, I see two options. You could separate this fraction into two separate fractions, but I definitely see an identity in that numerator. There's a Pythagorean identity, and so I'm going to use that one, the one that says 1 plus tangent squared equals secant squared. And so you see if I subtract 1 from both sides of this equation, then I get the fact that tangent squared equals secant squared minus 1. So I'm using this identity. And I'm just going to replace secant squared right here with tangent squared. Just to put a little note in here what I'm doing. Now, tangent squared over secant squared, is that equivalent to sine squared? Can't tell quite yet, so we're going to try to simplify it some more. And where my mind is taking me is to separate this fraction. So to rewrite it as tangent squared times 1 over secant squared. So secant squared was in the denominator, so when I separate it, it still needs to be a denominator. And I'm just carrying the right side down so I can keep track of where I'm trying to go. Okay, so I split these up because I know 1 over secant squared is cosine squared. So I'm using this just as a reciprocal identity. So I hope that this is easy. So just like a little explanation of what I'm doing. It's not part of my solution. All right, so this is going to give me tangent squared. And then this 1 over secant squared is going to become cosine squared. Okay, almost there. And here's one of the cases where writing everything in terms of sine and cosine might make things easier. So I don't want that tangent. I'm going to rewrite it in terms of sine and cosine. So here's the identity that I'm using. In this case, I'm going to use the fact that tangent is sine over cosine. So I'm just rewriting the tangent here. And that's going to give me sine squared over cosine squared times cosine squared. And now I've got something that can cancel out. I got a cosine squared on the top. I got a cosine squared on the bottom. These are factors. I don't have any addition or subtraction, so I can cancel these. That just leaves me with sine squared on the left and sine squared on the right. So I'll just rewrite it, but I got the left side to equal the right side, and I've shown that that is true. All right, another example. Lots of options here. I can see that, well, I'm going to be working with the left side. It's more complicated. And if I'm thinking about multiplying those two together, and I can tell that that's just going to make things more complicated. So I'm not going to do that. However, I see in each parentheses here these squares, and I'm thinking Pythagorean identities. So I'm going to take a look at my Pythagorean identities. And I do indeed have one that says 1 plus tangent squared is equal to secant squared. So I'm going to go ahead and make that substitution. So secant squared x is equal to all of that. Now I also have one that involves cosine squared. One last section we solved sine squared plus cosine squared equals 1, so that it said cosine squared minus 1, and that was equal to negative sine squared x. But don't take my word for it. Make sure that makes sense to you, and you can recreate that. Okay, so now what I got on the left side, if I multiply those two together, then I would just get negative secant squared times sine squared. So that's not getting tangent back. So I'm going to put both of these, I'm going to write in terms of sine and cosine. So I'm going to rewrite the secant squared. I'm going to use the reciprocal identity that secant is equal to 1 over cosine. So this is going to be 1 over cosine. And I'm not changing the sine squared because I want this left side to be in terms of sine and cosine. I don't want to mix up the reciprocals and the original functions. That makes sense. Because now you can see that when I multiply these two together, remember this is like denominator 1. So I just multiply top times the top and bottom times the bottom. And I get negative sine squared x over cosine squared x. And now I'm starting to see that this is going to equal tangent squared because I know sine over cosine is tangent. And I'm doing that twice. So I got tangent squared. And it's not. You could throw in an extra step here. You need to convince yourself or make it clear that these two are equal. But that's it. All right, here's another example. And this one would not be intuitive to me right away. It would take some experience to have this idea of how to solve this one. So I'm going to use the left side as terms, that addition and subtraction, that addition on the left side. I'm going to try to simplify that into one term. But I can't add a tangent and a cotangent. And maybe I could rewrite the cotangent as 1 over tangent, but I still wouldn't be able to add them. So I'm going to have to get a common denominator. And because looking at the right side and where I'm trying to go, that's secant and cosecant. And those are related to sine and cosine. I think this is the time that it would be beneficial to rewrite these in terms of sine and cosine. So I'm using reciprocal identities and the quotient. No, I'm using quotient. Using quotient identities to rewrite tangent as sine over cosine. And rewrite cotangent as cosine over sine. Okay, now I want to add these two fractions together, so I have to get the denominators to be the same. And the common denominator is just going to be the product of these two. So sine times cosine is the common denominator. So I'm just going to multiply each fraction by what it's missing. In my first fraction, the denominator is cosine, so it's missing sine. So I'm multiplying the top and the bottom. Got to do both by sine. In the second fraction, denominator is already signed. What it's missing is the cosine. So if I multiply this top and bottom by cosine, now my denominators are matched. So first fraction, in the numerator, sine times sine gives me sine squared. The denominator is sine x times cosine x. In the second fraction, cosine times cosine is cosine squared. Denominator is sine x times cosine x. So now denominators are the same. I can add them together. So adding them, I get sine squared plus cosine squared. We know what that's going to be. Keep the same denominator. Just bring it down the right side. And you don't necessarily have to bring down the right side at every step. Okay, but I know that sine squared plus cosine squared, that's a Pythagorean identity, is equal to 1. And maybe you can see it now. But I'm going to do one more step. I'm going to separate this into two fractions. So I'm going to do 1 over sine times 1 over cosine. So splitting it into two fractions. I'm going to double check. If I multiply these two together, would I get what I started with? The answer is there, but no. And you did something you're not allowed to do. Okay, so now I got my two fractions. And using reciprocal identities, 1 over sine is cosecant, and 1 over cosine is secant. And that is what I want. The order is not important because it's multiplication. The order is not important. 2 times 3 is the same as 3 times 2. So these two are equal to each other. And we're all done. Okay, one more example. And you should look at lots more examples. You should practice many, 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 many problems. And please feel free to ask me if you get stuck a lot, or you need some help, or you want to see something different, or you want to know what's the time when I would use this technique. Please let me know. I'm happy to help you. But this problem, similar to the last one, I've got these two terms on the right side, two fractions, and I want to try to combine them into one since I only have one term on the left side. So I'm going to be working with the right side. I'm trying to get, say, 2 secant squared x. Now with these two fractions, if I want to add them together, then they need the same denominator. Right now, denominators are, a little bit different, signs being different in the middle. But again, common denominator is going to be 1 minus sin x times 1 plus sin x. And I'm just going to multiply each fraction on the top and the bottom by what it's missing. So I'm going to make this enough steps up. Okay, this first fraction, what's missing in the top denominator is going to be 1 plus sin x. So I'm going to multiply top and bottom by 1 plus sin x. And then in the second fraction, the denominator is going to be missing the 1 minus. So I'm going to multiply the top and bottom by that. So I'm doing this because I need a common denominator if I want to add these fractions together. So this one's going to say 1 plus sin x. And for right now, I'm going to leave the denominators in factor form. Don't cancel anything. Uh-oh, I messed something up. This one should be plus. Okay, so this is plus. So plus. Okay, don't try to cancel anything because that's going to take you back where we came from. Instead, we're going to add them. So add in the numerators, the 1 plus sin x plus the 1 minus sin x. Just a note here that when you're subtracting, put the second numerator in parentheses. It's important for subtraction. But we're adding, so I'm too worried about it. Okay. Now I'm going to see, can I simplify or combine like terms in the numerator? And I can. I got these two ones. I can add them together. I get 2. I have 2 signs. I can add them together, but one's positive, one's negative, so they add up to 0. So I just have 2 over 1 minus sine x, 1 plus 2, which is not what I wanted. This doesn't get me where I want it to go. So I am going to multiply this denominator together. So foiling it together, 1 times 1 times sine, minus sine times 1, and minus sine times positive sine is a negative sine. Okay, so let's simplify that because these signs in the middle will cancel each other, and that'll leave us with a 1 minus sine squared x. Hopefully that was familiar. That's going to be related to this Pythagorean identity. If we subtract the sine x on both sides, then we get 1 minus sine x equals cosine squared. So this is 2 over cosine squared x. Okay, so almost where we want to be at 2 times secant squared. And it's in there. If I separate this, it's 2 over 1 times 1 over cosine squared. So cosine's still in the denominator. But 1 over cosine squared is secant squared. And that's what I wanted. So just verified. 2 secant squared, got it.